You're 11 billion miles from where you're sitting right now, and the light leaving your porch light this second will not catch up to where this spacecraft is for close to 19 and a half hours. Somewhere out there, a machine roughly the size and weight of a small car just crossed a boundary you cannot see, cannot photograph, and cannot feel. And on the other side of it, the universe stopped behaving the way it behaves anywhere near Earth. This is the story of what Voyager 2 actually found when it finally broke through the edge of the sun's own bubble, told with the real numbers, the real dates, and none of the exaggeration. If you're new here, this channel exists to give deep space missions the long, careful, fact-checked story they deserve. So if that's the kind of thing you're into, go ahead and subscribe before we get into it. Voyager 2 launched on August 20th, 1977 from Cape Canaveral, 16 days before its twin, Voyager 1, even though Voyager 1 ended up arriving at Jupiter first because it was placed on a faster, more direct trajectory. Both spacecraft were built by the Jet Propulsion Laboratory, each weighing about 815 kilograms at launch, and each carrying 10 identical scientific instruments designed to study planets, magnetic fields, cosmic rays, and plasma. The entire mission existed because of a rare planetary alignment discovered in 1965 by a graduate student named Gary Flandreau, who realized that Jupiter, Saturn, Uranus, and Neptune would line up in the late 1970s in a way that happens only once every 175 years, letting a single spacecraft use each planet's gravity to fling itself toward the next one instead of relying on rocket fuel alone. NASA called it the Grand Tour, and Voyager 2 remains, to this day, the only spacecraft ever to fly past all 4 of the outer giant planets in a single mission. The original mission was budgeted at roughly $250 million, and it was overseen for decades by project scientist Ed Stone, who joined the mission before launch and stayed with it until his retirement in 2022, spending well over half his working life following 2 spacecraft he would never see land, dock, or return. It reached Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989, and along the way it rewrote entire chapters of outer solar system science. At Jupiter, it captured evidence of active volcanoes on the moon Io, the first confirmed active volcanism found anywhere beyond Earth. At Saturn, it studied the planet's rings and atmosphere in detail no ground-based telescope could match, revealing ring structure that had never been visible from Earth at all. At Uranus, which no other spacecraft has visited before or since, it discovered 10 new moons and measured a magnetic field tilted almost 60 degrees off the planet's own rotation axis, something nobody had predicted, and nobody has been close enough to independently verify in the decades since. And at Neptune, its final planetary target, Voyager 2 discovered the Great Dark Spot, a storm system larger than Earth that later observations from the Hubble Space Telescope found had simply vanished, along with 6 previously unknown moons including Despina, Galatea, Larissa, Proteus, Naiad, and Thalassa. It also detected lightning-like discharges in Neptune's atmosphere and measured plasma wave activity at a sampling rate of nearly 29,000 samples per second. Data researchers are still referencing decades later when modeling how ice giant magnetospheres behave. Every one of those results was radioed home using an onboard computer system with a combined memory measured in kilobytes, not gigabytes, running code written and tested years before the spacecraft had ever left the ground, with no realistic option to patch that software once the spacecraft was too far away to fix in person. By the time it left Neptune's system in 1989, Voyager 2 had already earned its place in the history of space exploration. Its primary mission, complete 12 years after launch. What almost nobody expected, including many of the engineers who built it, was that the machine would still be working and still be discovering things 37 years later. Both Voyagers also carry something that has nothing to do with plasma physics at all. A gold-plated phonograph record assembled under the direction of astronomer Carl Sagan and a team at Cornell University, containing greetings recorded in 55 languages, natural sounds like wind, thunder, and birdsong, and 90 minutes of music spanning cultures and centuries, sealed with playback instructions etched directly into its cover on the extremely small chance that something, someday, finds it drifting through the galaxy long after Earth itself has changed beyond recognition. Once the planetary flybys ended, both Voyagers turned toward a much harder target, a boundary scientists call the Heliopause. To understand why that boundary matters, picture the sun constantly exhaling a stream of charged particles called the solar wind, blasting outward in every direction at hundreds of kilometers per second, fast enough to cross the distance from the sun to Earth in roughly 2 to 4 days. That wind inflates a colossal magnetic bubble around our entire solar system called the heliosphere, and everything inside that bubble, every planet, every asteroid, every one of us, lives inside the sun's direct influence, partially shielded from the harsher radiation environment of the wider galaxy. The heliosphere isn't a perfect sphere either. As the sun moves through the Milky Way, dragging its bubble along behind it, The heliosphere gets compressed on the leading side and stretched into something closer to a long tail on the trailing side, more like the wake behind a slow-moving ship than a balloon floating in still water. The heliopause itself is the point where the outward pressure of the solar wind finally loses its fight against the inward pressure of the interstellar medium, the thin, cold soup of gas and cosmic rays that fills the space between stars. Cross that line, and you're no longer inside the sun's bubble at all. You are, in a very real physical sense, outside the neighborhood the sun controls, standing in the same interstellar material that drifts between every other star in this part of the galaxy. Voyager 1 crossed that line first, in August 2012, at a distance of about 122 astronomical units from the sun, with one astronomical unit equal to the roughly 150 million kilometer distance between Earth and the sun. But Voyager 1's plasma instrument had stopped functioning correctly back in 1980, so scientists had to infer that crossing indirectly, through a sudden spike in cosmic ray counts and a drop in solar particles, and it took nearly a year of internal debate before the team felt confident enough to announce it publicly. That left an open scientific question that mattered enormously. Was what Voyager 1 detected a universal feature of the heliopause, something any spacecraft would find at that boundary, or was it something specific to the location and moment Voyager 1 happened to cross? Only a second, independent measurement, from a different direction and a different point in the sun's activity cycle, could actually answer that. Voyager 2 provided that second measurement on November 5, 2018, at a distance of 119 astronomical units from the sun, a little over 11 billion miles. And unlike its twin, Voyager 2's plasma science instrument was still fully operational at the time, which meant this crossing wasn't an inference built from indirect clues. It was measured directly, in real time, by an instrument built specifically to detect exactly this kind of transition. Here is where the actual discoveries begin, and each one builds directly on the last, because no single measurement told the whole story on its own. The first discovery is the crossing itself and the sheer suddenness of it. Over the course of about 5 days at the start of November 2018, Voyager 2's plasma detectors recorded density climbing from roughly 0.002 particles per cubic centimeter to nearly 0.093 particles per cubic centimeter, close to a 5-fold increase, while the outward radial speed of the solar wind dropped from about 74 kilometers per second down to effectively 0. A boundary that scientists had modeled and predicted for decades turned out to behave almost like a hard edge rather than a slow fade, with the final transition happening in under a day. And Voyager 2's instruments caught the entire event as it unfolded, rather than reconstructing it afterward from secondhand clues, the way the team had been forced to with Voyager 1. 3 sunward-pointed detectors on the plasma instrument, the ones that had spent decades tracking the outward flow of the solar wind, effectively went quiet within days of the crossing, because there was no more outward solar wind left in that direction to detect. That silence, on instruments that had been reliably humming with data since 1977, was itself one of the clearest signals the team had that Voyager 2 had actually left the heliosphere behind. The second discovery is the one that genuinely surprised the science team because it revealed structure nobody had directly measured before. Using its plasma wave subsystem, which detects density by listening to the natural oscillations of the plasma itself rather than counting particles directly, Voyager 2 found that the boundary wasn't a single clean line at all. About 5 astronomical units before the official heliopause, the plasma began slowing down, heating up, and becoming roughly twice as dense as the typical solar wind found deeper inside the heliosphere, a region researchers now call the boundary layer. Then, only about on the 0.06 astronomical units before the true crossing, a second, much thinner and sharper layer appeared, where density and magnetic field strength spiked again in a matter of hours. In other words, the edge of the solar system is layered, like scar tissue formed in stages rather than a single clean cut. And Voyager 2 is the only spacecraft in history to have flown directly through that layered structure with a working plasma instrument recording every stage of it. Researchers had actually seen faint hints of a similar layered transition 25 years earlier, when both Voyagers remotely detected unusual radio emissions, consistent with a boundary layer, long before either spacecraft got anywhere near it, but those early signals were indirect, recorded from tens of astronomical units away, and could only be confirmed once an actual spacecraft flew through the structure itself and measured it directly, which is exactly what Voyager 2 finally did in 2018. The third discovery concerns temperature, and it is arguably the most counterintuitive result to come out of the entire crossing. Based on existing models of the interstellar medium, scientists expected the plasma just outside the heliopause to sit somewhere between 15,000 and 30,000 degrees Celsius, cool enough that it comfortably fit prior assumptions about how quiet interstellar space should be this close to a relatively calm, middle-aged star like the Sun. Instead, Voyager 2 measured temperatures ranging between roughly 30,000 and 50,000 degrees Celsius, close to double the upper end of what models had predicted, and warm enough that researchers had to revisit assumptions that had gone essentially unchallenged since before Voyager 1 made its own crossing in 2012. The leading explanation, based on analysis the mission team published afterward, is that the ongoing collision between the Sun's magnetic field and the galaxy's magnetic field compresses the plasma right at that seam, and that compression heats it well beyond what a calm, undisturbed patch of interstellar space would ever reach on its own. So the very edge of our solar system isn't the cold, quiet frontier science fiction tends to imagine. It's a compressed, actively heated boundary, shaped by two enormous magnetic fields, still fighting over the same patch of space, and that heat signature turned out to be one of the clearest pieces of evidence that the transition really was a genuine physical seam between two different environments, rather than a soft, arbitrary line drawn on a map for convenience. The fourth discovery is about something the boundary was expected to do, and conspicuously did not do. For years, some theoretical models predicted that the heliopause should act like a kind of magnetic filter, twisting or rotating the direction of the magnetic field sharply as particles pass through it, the way a filter changes the character of whatever passes through its mesh. Voyager 2's magnetometer found something quieter and, in its own way, more interesting. The magnetic field direction measured just outside the heliopause lined up closely with the field direction measured just inside it, without the dramatic rotation many models had predicted. Combined with similar data gathered by Voyager 1 6 years earlier at a completely different point along the boundary, that result told scientists the sun's magnetic influence doesn't simply switch off at the boundary like a light going dark. It bends and drapes around the entire heliosphere in a way that still leaves a measurable signature well outside it, meaning the line between solar territory and interstellar territory is considerably fuzzier, magnetically speaking, than the sharp plasma transition alone would suggest. That single result forced several existing heliophysics models back to the drawing board because a filter that doesn't filter is not a small detail. It changes how researchers describe the physical shape of the boundary itself, from a hard magnetic wall into something closer to a porous seam where two separate magnetic environments quietly overlap rather than cleanly separate. The fifth discovery is the one NASA's own mission team described using the word leaky, and it may be the most conceptually important of the group. One of Voyager 2's particle instruments detected a small but measurable trickle of particles that originated inside the heliosphere, slipping outward through the boundary into interstellar space, even well after the official crossing had already happened. The heliosphere, it turns out, does not behave like a sealed bubble with a hard, impenetrable shell. It behaves more like a ship's hull with slow, persistent leaks, letting a thin, continuous stream of solar material bleed into the surrounding galaxy. 5 separate research papers, each describing results from a different one of Voyager 2's science instruments, were published together in the journal Nature Astronomy in November 2019, and taken as a complete set, they didn't just confirm what Voyager 1 had found in 2012. They turned a single, debated data point into an actual evidence-backed picture of how a star's magnetic bubble interacts with the wider galaxy around it. Something no textbook could have described with this level of precision before either Voyager physically flew through it. The Johns Hopkins Applied Physics Laboratory, which helped operate several of the instruments involved, described the relationship this way at the time, comparing the heliosphere to a ship sailing through interstellar space, with the newly discovered leak acting like water, slowly finding its way through a hull that had long been assumed watertight. The sixth discovery only becomes visible once you put both crossings side by side, 7 years and a completely different point on the heliosphere apart. Voyager 1 exited near the nose of the heliosphere, the leading edge pushing forward through the interstellar medium as the entire solar system moves through the galaxy, while Voyager 2 exited from a different angle entirely. Despite that difference in geometry, and despite crossing during a different phase of the Sun's roughly 11-year activity cycle, both spacecraft measured a heliopause sitting at a broadly similar distance, 122 astronomical units for Voyager 1 and 119 for Voyager 2, and both found broadly similar density jumps at the crossing itself. That consistency across 2 different locations and 2 different solar conditions is what let scientists finally treat the heliopause as a real, physically consistent structure rather than a one-time anomaly Voyager 1 happened to fly through. Without Voyager 2's independent confirmation, researchers would still be arguing about whether 2012's data described the edge of the solar system or just an unusual patch of space Voyager 1 happened to wander into. It's worth remembering, too, that 2 earlier NASA probes, Pioneer 10 and Pioneer 11, launched even before the Voyagers, in 1972 and 1973, and both eventually lost contact with Earth decades ago without ever confirming a heliopause crossing of their own, their power supplies simply running out too soon. That makes the Voyagers not just the first spacecraft to reach interstellar space, but so far the only ones that have ever survived long enough, with enough working instruments to actually prove it happened. So why does any of this matter to you? A person who almost certainly isn't building spacecraft or reading plasma physics journals in their spare time? Here is the precise, grounded answer without inflating it into something it isn't. The heliosphere functions as a partial radiation shield for the entire solar system. Measurements from both Voyagers have shown that this bubble blocks a majority of galactic cosmic radiation, the high-energy particles produced by exploding stars and other violent events scattered across the galaxy, from ever reaching the inner solar system where Earth and every crewed spacecraft currently operates. That shielding effect matters directly for how much radiation astronauts absorb on long-duration missions, and for how engineers calculate radiation protection requirements for any future crewed mission beyond low Earth orbit, whether that's a sustained lunar presence or an eventual crewed trip to Mars, where astronauts would spend months traveling through open space with far less protection than they currently have living inside the International Space Station's low orbit, which sits well within the reach of Earth's own additional magnetic field. Voyager 2's direct, in-place measurements of density, temperature, and the layered structure of the boundary give mission planners real physical numbers to design around instead of purely theoretical estimates, because for the first time in history, we know what the edge of that shield actually looks like from both the inside and the outside, measured by an instrument that was physically present when it happened. That is the concrete, defensible change. It does not rewrite biology, it does not rewrite gravity, and it says nothing at all about life beyond Earth. What it does is refine, with hard-measured data, exactly how protected the solar system is from the rest of the galaxy, and exactly how that protection tapers off once you leave it. There's a second, quieter implication worth naming as well. Every model of how stars interact with the interstellar medium around them, models used to study other stars and their own theoretical heliospheres across the galaxy, now has two real, physically measured anchor points to calibrate against instead of pure theory. Astrophysicists studying stellar winds around entirely different stars, including younger, more active ones than our own Sun, use the Voyager crossings as a baseline for what a heliosphere boundary can realistically look like. Because until November 2018, nobody had ever measured one directly, twice, from the inside out. That is not a headline-grabbing kind of significance, but it is a durable one, the kind that quietly underpins other research for decades after the original data was collected. It is the difference between guessing what a star's protective bubble looks like from light years away and actually having a measured, physical reference point drawn from a spacecraft that flew through the boundary itself, felt the temperature spike, and radioed the numbers home. Now for where things actually stand this year. Both Voyagers are still operating, remarkably, nearly 49 years after launch, but they are running out of electricity, not fuel. Each spacecraft carries 3 radioisotope thermoelectric generators that convert heat from the decay of plutonium into electrical power, producing about 470 watts combined at launch in 1977, a figure that halves roughly every 87. 7 years as the plutonium naturally decays, meaning both spacecraft lose approximately 4 watts of usable power every single year. That sounds small, but 4 watts is enough to force engineers into difficult trade-offs. And it has been happening every year since the 1980s, when several planetary flyby instruments were already switched off, simply because they weren't needed once Neptune was behind the spacecraft. To stretch the mission as long as physically possible, NASA's engineering team has been shutting down remaining instruments one at a time, in a carefully sequenced order based on which data still matters most for interstellar science. In April 2023, engineers found a way to tap into a small reserve of backup power originally set aside for an onboard safety mechanism, a move that bought both spacecraft roughly 3 additional years of operation they otherwise wouldn't have had. Voyager 2's plasma science instrument, the very one that recorded that dramatic 5-fold density jump back in November 2018, was powered down in October 2024 to conserve energy for the instruments considered more essential to ongoing interstellar studies. Its low-energy, charged particle instrument, which measured ions, electrons, and cosmic rays from both the solar system and the galaxy, using a rotating platform that scanned a full 360 degrees every 192 seconds, was switched off in March 2025. Its cosmic ray subsystem is scheduled for shutdown sometime in 2026. That will leave Voyager 2 running on just its magnetic field instrument and its plasma wave subsystem, the same 2 systems responsible for several of the discoveries in this video, and mission engineers, including project manager Suzanne Dodd and project scientist Linda Spilker, believe those 2 instruments could keep returning usable science data into the early 2030s. As of early 2026, Voyager 2 sits at roughly 142 astronomical units from the Sun, more than 21 billion kilometers away, moving through the direction of the southern constellation Pavo, so distant that a radio signal traveling at the speed of light takes close to 19.5 hours to reach it, and just as long again to bring an answer home. Voyager 1, for comparison, is now approaching 1 full light day from Earth, a distance NASA expects it to cross in mid-November 2026, becoming the first human-made object ever to reach that milestone. Both spacecraft are also dealing with an aging propulsion system, and in recent years, engineers uploaded new thruster control software specifically to slow the gradual clogging of the tiny fuel injectors that keep each spacecraft's antenna pointed at Earth, a fix tested on Voyager 2 first, precisely because it is close enough that a mistake could still be corrected before being attempted on the more distant Voyager 1. What we still don't fully understand is where the true character of the interstellar medium itself settles down, since the region just beyond the heliopause has turned out to be far more variable and turbulent than early models assumed, with density and temperature readings that shift more than expected as both spacecraft continue moving deeper into it. We don't yet know precisely what mechanism is driving the plasma compression detected on both sides of the boundary, only that both Voyagers measured it independently. And nobody, including the mission's own project scientists, knows exactly how many more years either spacecraft has left, because the honest, stated position from the team is that every day of operation at this point counts as bonus time on hardware that was never designed to function for 5 decades in one of the coldest, most isolated environments a human-made object has ever occupied. NASA's own projections suggest both spacecraft could remain within range of the Deep Space Network through roughly 2036, but that number depends entirely on how much electrical power is left to push a signal across 11 billion miles of empty space. There is no successor mission currently flying that would repeat this exact kind of direct, in-place measurement of the heliopause from multiple independent directions, which means whatever these two aging spacecraft measure between now and their final transmission may stand as the only ground truth data of its kind for an entire generation of scientists to come. NASA and Johns Hopkins researchers have studied concepts for a dedicated interstellar probe, a future spacecraft purpose built to reach and cross the heliopause faster and with more advanced instruments than a machine designed in the 1970s ever could. But as of now, that mission exists only as a proposal without a confirmed launch date, meaning the earliest a true successor could realistically fly is sometime in the 2030s at best. Until a mission like that actually launches, everything we know about crossing the edge of the solar system from direct measurement, rather than distant observation, still comes from exactly 2 machines, both of them older than most of the engineers currently keeping them alive. Any proposed interstellar probe would also need decades just to reach the boundary Voyager 2 crossed in 2018, since even traveling faster than either Voyager, a new mission launched in the 2030s likely wouldn't reach the heliopause itself until sometime in the 2050s or later, which means for the next several decades at minimum, Voyager 1 and Voyager 2 will remain the only direct witnesses humanity has ever sent to that boundary. 2 machines designed and built in the 1970s, using less onboard computing power than a modern digital thermostat, are still out there right now, past the edge of the sun's protection, quietly logging measurements of a boundary that no human being will personally reach in any of our lifetimes, and very possibly never. Each one still carries its golden record, the phonograph disc encoded with sounds and images of Earth, sealed and waiting for an audience that may never come, spinning through the dark at over 15 kilometers every second without a single hand ever touching it again. Every signal either spacecraft sends back left it nearly a full day ago, crossing a stretch of space where, for the first time in either mission's history, there is no more sun standing between them and the rest of the galaxy at all. Somewhere in a control room at the Jet Propulsion Laboratory, an antenna the size of a football field is still listening for a signal from an object launched before most of the people currently monitoring it were even born. And for now, against every reasonable expectation from 1977, that signal is still arriving. If this kind of deep-sourced space story is your thing, subscribe so you don't miss the next one, drop a comment with what mission you want covered next, and share this with someone who'd actually want to know what's happening at the true edge of our solar system.